Unit 3, this video will talk about learning target 3b, which is all about the derivatives of exponential and logarithmic functions. So in our last learning target, we learned how to take the derivative of all 6 trig functions, and in this section we're going to continue to build upon that and learn about how to take the derivative of an exponential function with either base e or with base a, where a could be any positive number as our base, and then we'll also learn how to take the derivatives of a natural log and a log base a function as well. So for the derivative of an exponential function with base e, we will be using the chain rule for all of these since we have a composition of functions. So when we're taking the derivative of e to the x with respect to x, that is e to the x times the derivative of the exponent, which in this case would be 1 since the derivative of x is just 1. Now we're going to look at that more generalized. So if I have e to the u, where u could be any function in terms of x, then the derivative of e to the u with respect to x would be e to the u times, using the chain rule, the derivative of u with respect to x. So this du over dx we did see in our last learning target, and it just represents the general derivative of u with respect to x, depending on what that function is in our exponent. Let's do some practice problems here. So in our first example, we have the function y equals e to the 5x, and we're asked to differentiate this function. So we need to find its derivative. So I'm going to call it y prime. I could also call it dy over dx. Now since I have an exponential function, I don't have a product of anything, I just have a single exponential function of e to the 5x. The derivative of that function would be e to the 5x times the derivative of the exponent here, and the derivative of the exponent would be 5, since the derivative of 5x is going to be 5. And a lot of the time you'll see this rewritten as 5 times e to the 5x, since we usually move the scalar down in front. So as you guys continue to practice these, it might just become habit that you put the coefficient in front, and that's how you would see it on like a multiple choice version as you're trying to have it match. Let's look at example B. So in example B, we have y equals 4 times e to the x squared. So I do have a scalar here of the 4 coefficient in front. That's not going to make a difference. I still can find my derivative. Call it dy over dx this time. I could have called it y prime. Those two notations are interchangeable. The 4 is going to go along for the ride since it's a coefficient. Derivative of e to the x squared is e to the x squared times the derivative of the exponent, and the exponent here is x squared. Derivative of x squared would be 2x. And we could simplify this down a little bit and multiply the 4 and the 2 and get an 8x e to the x squared. So although on free response we would not need to simplify our answer, if it was a multiple choice problem we would have to make it match. So I do want to continue to talk about how we can simplify these down a little bit. So look at example C here. We have y equals e to the x plus 3x squared. So this whole x plus 3x squared is in our exponent there. So when we go to find our derivative, I'll call it dy over dx again. The derivative of any exponential is the function itself. So I still have the e to the x plus 3x squared times, now I have to take the derivative of the exponent. Since the exponent here is a sum of two functions, I'm going to need parentheses around that derivative since the whole derivative needs to be multiplied to the e to the x plus 3x squared. Our derivative of our exponent there would be 1 plus 6x by using the power rule. And yes, these parentheses would be necessary since both the 1 and the 6x are being multiplied to this e function. Okay, let's look at example D. So in example D here, we see that we have a trig function as our exponent. So we are going to incorporate all the trig functions that we learned about in that last section because we can build upon all of these functions and kind of combine them together. So in this section, in this problem, we have y equals 3 e to the sine of x. So I have a scalar again, so that scalar is just going to go along for the ride, so the 3 will still stay there. Derivative of e to anything is that exact same function, so e to the sine of x again, times the derivative of the exponent. We know from our last section that the derivative of sine is cosine. And then this itself is a chain rule since I have an inside function here of x and the derivative of x there is 1. So we end up with 3 times e to the sine of x. Derivative of sine of x is cosine of x times the 1 from the derivative of that inside function. So this was actually a double chain rule in there since my exponent itself was a composition of functions as well. Although in this case the 1 is not going to make a difference since multiplying by 1 won't change anything, but we do want to keep that in mind in case I didn't just have an x inside my sine function. Okay, let's look at example E. So in example E, we have y equals 4x plus 1 times e to the x to the 5th. Well, here I have a product of functions since I have this 4x plus 1 and that exponential function. What rule or rules will I have to use to take the derivative of example E? So in this case, I'm going to have to use a product rule. Since I have a product of functions, I will also be using a power rule and a chain rule as well. So the product rule tells me that I take the derivative of the first function. So our first function here is 4x plus 1. The derivative of that function would be 4. Keep the second function the same, so I just rewrite the e to the x to the 5th. Plus, now I'm going to keep my first function the same, so 4x plus 1. Times, now I get to take the derivative of e to the x to the 5th. Well, to take the derivative of e to the x to the 5th, I have to use a chain rule. I know I get the original function, e to the x to the 5th, times that derivative of that exponent there, and the derivative of x to the 5th would be 5x to the 4th. So we can see how we can not only incorporate our trig functions, but we can also incorporate product rules, quotient rules, and our power rules that we've been using all along as well. Okay, let's look at example F. So we have the function y equals 3x over e to the x. There's a couple ways to approach this. We could use a quotient rule as it stands right now, but I want us to instead think about how we could rewrite this without a fraction. So to rewrite anything without a fraction there, I can move the denominator up to the numerator by making that exponent negative. So I would end up with 3x times e to the negative x there if I were moving that e to the x up to the numerator. This will now make this a product rule instead of having to be a quotient rule. Why don't you guys pause the video and find your derivative for this last example here. Let's check our derivative. So using the product rule, I have the 3x as my first function. Derivative of 3x is 3. Keep the second function the same, so the e to the negative x stays the same, plus my first function of 3x times, now I get to take the derivative of e to the negative x. Well, e to anything, that derivative is itself, so I get e to the negative x times the derivative of the exponent there, which would be negative 1. We found our derivative for our last example here, and we had to use that product rule since we had this function 3x times the separate function e to the negative x. If you didn't want to rewrite it, you could have used a quotient rule as well. That would work the same, and if you were to simplify it down, they would end up with equivalent answers. Let's look at what happens if our base now is no longer base e. So if I have a base, and I'm going to use a as my base here. So a is representing any positive number that's not equal to 1, and I'm assuming it's not e either. The derivative of a to the x is going to be a to the x. So it's similar to what we had with our e to the x times the natural log of a times the derivative of the exponent there, which would be the 1. If we do this in general and I take the derivative of a to the u with respect to x, where u is again any function in terms of x, I would get a to the u times the natural log of our base, which is a, times the derivative of u with respect to x. Now we actually did this up above, but I didn't have to worry about that natural log of the base part because, as a little reminder here, the natural log of e is equal to 1. So technically I am multiplying by the natural log of e, but since the natural log of e is 1, it doesn't change anything. But if I have a base down here that is different than e, like 2 or 5 or maybe 10, I need to make sure that I'm taking into account natural log of that base, since that is going to end up being a scalar that will affect our derivative there. So the natural log of a is a number, it's not a function, it would be an irrational number. Okay, let's look at some examples. So in our second set of examples, we're asked to differentiate each of the functions, so we're finding their derivatives. Let's start with our first function. We have y equals 2 to the 6x power. So if I'm going to take the derivative there, I can find my dy over dx. 2 here is my base, and 6 times x is going to be my exponent. So I know that I get that exact same function back of 2 to my exponent times now the natural log of my base, so natural log of 2 times the derivative of the exponent would give us a 6. And if we were to try to simplify this down, I can't actually combine or multiply any of these terms. So the natural log of 2 times 6, I can't multiply those. I could make the 6 an exponent on the 2 by using properties of logs, but there's no need to do that. I also cannot multiply the base here of 2 with this coefficient of 6. Those cannot get multiplied. Let's look at our second example with this. So we have y equals 4 to the exponent here that got a little bit more complicated, 5x minus x cubed. Why don't you guys pause the video and find your derivative for example B. So our derivative here, we have 4 as our base and the 5x minus x cubed as our exponent. So I'll get that exact same function back, 4 to this exponent, times the natural log of our base, which would be the natural log of 4, times the derivative of the exponent here. And we're going to want to make sure we have that derivative of that exponent in parentheses, since I will have two terms. And that derivative will be 5 minus 3 times x squared by using the power rule. Let's look at example C. So example C here says y equals 3 to the cosine of x. So again, we can include our trig functions and kind of incorporate all of these types of functions together. So let's find our dy over dx, or our y prime, whatever you want to call it. Why don't you guys pause the video and find the derivative of 3 to the cosine of x power. So to do that, our base here is 3, our exponent is cosine of x, so I'll get 3 to the cosine of x again, times the natural log of the base, so natural log of 3, times the derivative of the exponent. And the derivative of cosine is negative sign. I have to keep the inside function the same, times the derivative of the inside function, which is 1, from that derivative of that x. So we do want to keep in mind that our chain rule is still definitely relevant in this section, especially if we're incorporating trig functions, although the multiplying by 1 won't change anything. If this was cosine of, let's say, x squared, then I want to make sure I'm taking into account the derivative of the inside function. Let's look at our last example on page 80. So we have y equals sine of 4x times 5 to the x minus 3 power. Here we have a product of functions, since we have the sine of 4x times this exponential function. So we're going to have to use a product rule when we take this derivative. Why don't you guys pause the video and find our derivative for the function in example D. Okay, let's check our derivative. So using the product rule, I'll start with the derivative of the first function. To take the derivative of sine of 4x, I'll be using a chain rule. Derivative of sine is cosine. Keep the inside the same, so the 4x stays the same, times the derivative of the inside would be the derivative of 4x, which is 4. Then times the second function, so times that 5 to the x minus 3, plus now I keep the first function the same, so sine of 4x will stay the same. Now I get to take the derivative of 5 to the x minus third power, so the derivative of that would be 5 to the x minus 3 times the natural log of the base, which would be the natural log of 5, times the derivative of the exponent there is actually just a 1. So because we had that product of functions, I had to make sure I'm using our product rule. So we're taking the derivative of one term at a time, or one function at a time, keep the other guy the same, plus flip-flop which one you're taking the derivative of. And if you were to simplify any of this down, I do want to point out that this 4 and this 5 cannot get multiplied. That 4 is a coefficient and the 5 is a base. I cannot multiply those numbers. All I could really do, if I'm going to kind of rewrite this and make it look a little bit cleaner, I would probably move the 4 in front and have 4 times cosine of 4x times 5x to the negative third, which I know doesn't change anything, it's just redoing the order in which I multiplied them. And then over here, that ln of 5 is my scalar on the second term, or my coefficient. So I have the natural log of 5 sine of 4x times that 5x to the x minus third power. And there's nothing else I can combine here. I guess I could factor out the 5 to the x minus 3, but it's not necessary on here. Okay, let's look at what happens with log functions. So we're going to start by looking at taking the derivative of our natural log function, and then we're going to look at what happens if I change the base. So remember, the natural log function has base e. So as a little recall here from algebra, if I had log log and the base was e of x, this is how we get the natural log function of x. So the ln represents our natural log, and it's a shorthand for saying log base e. So to take our derivative of a natural log, the derivative of the natural log of x is 1 over x times the derivative of the inside function, which would just be 1. If we do that more generalized and we're taking the derivative of the natural log of u with respect to x, our derivative of this would be 1 over u times the derivative of u with respect to x. And a lot of the time we could write this as one fraction if we wanted to, and have the derivative of u with respect to x all over that original input that we had of u. So again, these are going to be chain rules, and we're having to take into account that derivative of the input of our natural log. So let's look at example 3a. And all of these were asked to differentiate the following. In our first example, we have y equals the natural log of 4x squared minus 3x plus 1. So to find our derivative here, finding my dy over dx, since I have a natural log, the derivative of a natural log function is 1 over the inside stuff, so 1 over 4x squared minus 3x plus 1 times the derivative of the inside. So now I get to take the derivative of 4x squared minus 3x plus 1. That would be 8x minus 3. And a lot of the time, so that we don't have to write a fraction times another number constant here, we can have the 8x minus 3 just move to the top part of that fraction over the 4x squared minus 3x plus 1, if I try to fit it all there. So feel free to write these as one fraction where the numerator is the derivative of the inside. And to save a little bit of space, I'm going to start doing that as we move throughout the rest of these problems. So let's look at example B. We have y equals the natural log of 5x minus 1. And we want to find the derivative of that guy. Why don't you guys pause the video and find your derivative? Let's check our derivative. So to take the derivative of the natural log of something, it'd be 1 over that something, so 1 over 5x minus 1, times the derivative of the inside, so now I get to take the derivative of 5x minus 1, which would give me 5. And since I would have 1 times 5 in the numerator, I could just write that as 5. One thing I do want to point out is you cannot cancel these 5s because the bottom portion, the whole factor in the denominator is 5x minus 1, and it could only cancel if you had a 5x minus 1 in the numerator. So although it's tempting to want to say that I can cancel those 5s, I cannot do that because then I'm ignoring what's happening over here with the negative 1, which is part of that denominator. Okay, let's look at example C. So here we have the natural log of a square root of 2x minus 8. So this one's going to get a little bit more complicated, and we're going to actually have a double chain rule here that we're going to look at. So my outermost function here is the natural log. To take the derivative of the natural log, it is 1 over the stuff inside. So that square root of 2x minus 8. I would have 1 over that times, now I have to take the derivative of the square root of 2x minus 8. Well, let's think about how we could rewrite this. I could rewrite that square root as a 2x minus 8 to the 1/2 power. So from there, when I take the derivative of 2x minus 8 to the 1/2 power, that's another chain rule. So the 1/2 comes down, keep the 2x minus 8 the same, now to the negative 1/2, times the derivative of the inside there, which would be 2. And that is all in the numerator. Now, in case this was a multiple choice, we would need to know how to simplify this down. So let's take this kind of piece by piece. I have a 1/2 times a 2, so those guys will cancel since a half times a 2 will be equal to 1. The next thing that I can do is I can rewrite this negative exponent. So I'll still have that 1 over the square root of 2x minus 8 that we had to start with, times, if I rewrite the negative exponent, that can move down to the denominator, and that will also be 1 over the square root of 2x minus 8. Since the negative exponent, when I move it down, becomes positive, and then the 1/2 exponent is the same thing as a square root. Now from here, I could multiply these, and if I have the square root of something times itself, I end up with the square root squared, and those are inverse functions that cancel each other out, so I end up with 1 over 2x minus 8. So I do want us to be aware about how that could really simplify down a lot in case this was on a multiple choice problem and you got the original answer and then you're thinking, how can I have it matched to one of the options that are given? We just got to think about it, take it a step at a time, think about canceling any coefficients, and then how we could reduce down that negative 1/2 exponent and then multiply our like terms from there. Okay, let's look at example D. So in example D, we have y equals the natural log of sine of 3x. Again, we're going to have a double chain rule here. And the reason being is that I have the natural log as my outermost function. So we'll start with the derivative of the natural log. The derivative of the natural log is 1 over sine of 3x times the derivative of the sine of 3x. That in and of itself is also a chain rule. So the derivative of sine of something would be cosine, keep that inside the same, so cosine of 3x times the derivative of the inside there would be 3. Now if we were trying to simplify this one, I could rewrite this, I'll fit it underneath. I could move the 3 and the cosine of 3x all on top, all over sine of 3x, just by combining it down to be one fraction again. And then if we think about this, cosine of 3x over sine of 3x, since I have the same inputs here for my trig values, cosine over sine, we know is equal to cotangent, so I could simplify this all the way down to 3 times cotangent of 3x. So again, I'm just bringing these up in case they were a multiple choice question and we had to simplify it down to make the answer match. But if it's a free response problem, please do not simplify. And in fact, on your learning checks, the free response problems actually say that you should not be simplifying your answer because having all of your work shown is justifying that you understand what rules you're using and how to take their derivatives. Okay, let's look at what happens if we have a log with a different base here. So here we have log base a of x. So a here is our base, just like it was in our base of our exponent on the prior page. And we're just assuming that that base is not equal to 1 and that we also have a base that's not e, otherwise we could just use the natural log. So to take the derivative of log base a of x, it's similar to natural log. I still get 1 over the x, but I also have to multiply by the natural log of that base again. And if we scroll back up to the prior page, we did this with the exponential function, and I had to multiply that a to the x by the base of my natural log. The same thing happens here. I have to multiply the x by that base of that natural log of a. And then technically, I'm also multiplying by 1 from the derivative of the inside, which is that derivative of x. Now, if we generalize this, I can do the same thing. I'll have 1 over u times the natural log of the base, which is the natural log of a, times the derivative of u with respect to x, depending on whatever our function u is in terms of x. So let's do some of these examples. And again, I do want to point out we have the same derivative rule here, and we're just relying on the fact again that the natural log of e is equal to 1, so that's why I didn't have to worry about it in the natural log case. Okay, so let's look at some of these here. So our first function says y equals log base 5 of 7x. So our base here is 5 and our input is 7x. If we're going to find the derivative of this guy, we would get 1 over 7x, since that's our input, times the natural log of the base, so times the natural log of 5, all times the derivative of the inside, which is 7. And that I'm just going to put in the numerator there. Now in this case, this is different than this example up here, which was I think example B for the natural log functions. In the denominator here, since everything's being multiplied together, I can actually cancel the 7s. Those are allowed to reduce down since everything itself is a factor, and I would end up with 1 over x times the natural log of 5. Up here though with the 5s, I could not cancel these 5s because the 5x minus 1, those are two terms and it is not in factored form. Okay, let's look at example B. So in example B, we have log base 7 of 4 over x as our input. So as it stands right now, I could take the derivative, and then when I worry about the derivative of 4 over x, I'd have to use the quotient rule. So instead, I'm going to rewrite this to avoid the quotient rule, and I could rewrite this as log base 7 of 4 times x to the negative first. And this way, I just don't have to worry about a quotient rule when I take the derivative of the 4 over x. So if we're going to take our derivative here, our derivative of log base 7 of something will be 1 over that 4x to the negative first, so that original input, times the natural log of 7, in the denominator, then times the derivative of the inside, and the derivative of 4x to the negative first would be negative 4x to the negative second power. And this could also be simplified down quite a bit. I'm going to scroll down so we have enough space. The 4's could cancel since I have factors again, so the 4's can cancel. And then this negative x to the negative second, we could rewrite as negative 1 over x squared over, I could rewrite the x to the negative first as 1 over x, a natural log of 7 there. And from here, these do reduce down, and I just get left with a single x in the denominator. So this is equal to negative 1 over x times the natural log of 7. And what's happening there is if I multiply by the reciprocal of 1 over x, that x squared comes down to the denominator, and I end up with x over x squared, which reduces down to just be a single x in the denominator. Okay, let's look at example C. So now we have trig functions again. So we have log base 2 of cosine of 4x. So we are going to have a double chain rule here. Why don't you guys pause the video and find your derivative for this example C. Okay, to take our derivative here, I can have 1 over cosine of 4x, since that's our input to our log, times the natural log of our base, so the natural log of 2, and then we would have the derivative of cosine of 4x. Derivative of cosine is negative sine. Keep that inside the same, times the derivative of the inside there is 4. So we did have that double chain rule in play, so we would want to think about all of that that's involved. And the negative sine of 4x times 4 is coming from the derivative of cosine of 4x. Again, this one could also reduce down since sine of 4x and cosine of 4x have the same inputs. We know that sine over cosine is tangent, so we could rewrite this as 4 times tangent of 4x all over the natural log of 2. Okay, let's look at example D. So we have log of the cubed root of 5x minus 2. So a couple things to think about. The cubed root I'm going to rewrite as the 1/3 exponent, but I don't have a base written here. What is it assumed to be? What is our base that we're assuming if I don't have a base written, but I just have log, so log. So if we don't have a base written, we assume that our base is 10. So log of the cubed root of 5x minus 2 is the same thing as log base 10 of 5x minus 2 to the 1/3 power. Now we can take that derivative. So dy over dx, or our y prime, whatever you want to call it, would be 1 over this 5x minus 2 to the 1/3 power times the natural log of 10, since 10 is our base, times the derivative of that 5x minus 3 to the 1/3, which will be a chain rule as well. So the 1/3 will come down, keep the 5x minus 2 the same, to the negative 2/3, times the derivative of the inside there is 5. And just like we did up before I believe it was in example 3C, we could simplify this down further and rewrite this 5x minus 2, bring it down to the denominator, and when that happens, I'll have a 5/3 in the numerator right now, since I just have 5 times a third. Then I have this 5x minus 2 to the 1/3, and a 5x minus 2 to the positive 2/3 now. I still have that natural log of 10 as well, so it'll fit. Now when I multiply exponents that have the same base, I add their exponents. So what I end up with is 5/3. Actually, I'm going to make sure I have enough space. So when I multiply that 5x minus 2 to the 1/3 and 5x minus 2 to the 2/3, I'm adding the exponents. So I end up with 5x minus 2 to the first power, since 1/3 plus 2/3 is 1, or 3/3, which is 1, times that natural log of, not 5, of 10. So again, this does reduce down nicely, and for the 5/3 we could bring the 3 down to the denominator too if we wanted to, so that we don't have any fractions within fractions. So we had 5 over 3 times 5x minus 2 times the natural log of 10. Okay, so those are our 4 new rules for this section. Now we're going to see how we can combine a lot of those together. And one thing I do want to point out is that the derivatives of exponential functions with base e and the derivatives of natural log functions, those come up a lot. The other 2 rules can come up, but they're not as common as the first 2, since we do deal with natural logs and bases much more often. So let's look at example 5. We have y equals x squared times e to the 5x. What rule or rules do you guys think we're going to have to use to take our derivative here? So for this guy, we're going to need a product rule. We'll also use the power rule and a chain rule as well. So let's find our derivative. Because I have a product rule, I'm going to start with the derivative of the first function. So the derivative of x squared, that's 2x. Keep the second function the same, so e to the 5x stays the same, plus keep the first function the same, which is the x squared, times, now I take the derivative of e to the 5x. Well, the derivative of e to anything is e to that same anything, so e to the 5x times the derivative of the exponent, which would be 5. And on all of these, I am not going to simplify any of these as we're going. We're just going to have our derivative rules written out. So in example 5, we did need a product rule. We also used a power rule. We used power rule twice, and the chain rule as well. We took the derivative of e to the 5x. Okay, let's look at example 6. We have f of x equals x times the natural log of 7 minus 10x. What rule or rules do you guys think we're going to have to use to find our derivative for example 6? So we will need a product rule here, since I have x times the natural log of 7 minus 10x, so I have 2 functions. Why don't you guys pause the video and find your derivative in example 6. Okay, so to find our derivative here, start with the derivative of x, that's just going to be 1, times the second function, so the natural log of all of that, plus keep the first function the same, which is x, times the derivative of a natural log function is going to be 1 over the input, so 1 over 7 minus 10x, times the derivative of that 7 minus 10x, which would be negative 10. And that will be our f prime for example 6. Okay, let's look at example 7. We have y equals e to the tangent of 4x. What rule or rules do you guys think we're going to have to use to take our derivative for example 7? So in example 7 here, we will need a chain rule. It's actually going to be a double chain rule, since our exponent here is a trig function. So to take the derivative of e to anything, it's always going to be that e to that same stuff. So I get e to the tangent of 4x times the derivative of the exponent. So to take the derivative of tangent of 4x, I have a chain rule. Derivative of tangent is secant squared. Keep the inside the same, so the 4x stays the same, times the derivative of the inside there, which would be 4. So we can see how as we start to combine exponentials and trig functions and logs all together, we've got to be very careful and just make sure we're writing out each of these steps and thinking through all the chain rules or product rules and maybe even quotient rules that we might have. Okay, let's look at example 8. So example 8 says f of x equals 7 to the 4x times the natural log of secant of x. What rule or rules do you guys think we're going to have to use in example 8? So the first thing I notice is I have a product of two functions. I have 7 to the 4x times a natural log of secant of x. So I will definitely need a product rule here. So let's start with the product rule. That says I take the derivative of the first function. Well, to take the derivative of 7 to the 4x, I need the chain rule. So I'll get 7 to the 4x times the natural log of that base, since my base here is not e, so times the natural log of 7, times the derivative of the exponent, and the derivative of 4x is going to be 4. Now, multiply that to the original second function, so the natural log of secant of x doesn't change, plus now I keep the first function the same, and now I get to take the derivative of the natural log of secant of x. Well, to take the derivative of a natural log, I also need a chain rule. So the derivative of a natural log is 1 over that input, so I get 1 over secant of x, times, though, the derivative of secant, and the derivative of secant is secant tangent, and remember, both of those get the same input. So my original input was x, so both secant and tangent get that input of x, times technically the derivative of x, which is 1. Yeah, we could reduce some things down here with canceling the secants, but I am going to leave this completely unsimplified for us to see. Okay, let's look at example 9. So we have f of x equals 2 plus sine of 3x. All of that is being raised to the pi power. So I do have these parentheses here, and that pi is on the outside of those parentheses. What rule or rules do you guys think we're going to have to use to take our derivative in example 9? So in example 9, we're going to have to use a chain rule. And I have an outermost function here of the pi power, which sounds really weird. But remember, pi is just a constant. It's an irrational number. It's about 3.14. It does keep going, so that's just an approximation for it. But it's representing, and it works the same as if I had a power here. So if I just had a squared or a cubed power, I would use the power rule. I can do the same thing. It's just going to look a little bit funkier. So the pi comes down, and this whole stuff will be raised to the pi minus 1 power. Because what the power rule tells us is that I subtract 1 from my exponent. So if I started with an exponent of 3, I would have a 2 here since I did 3 minus 1. But since I have an exponent of pi, I can still do pi minus 1. I just can't simplify that down since pi is irrational. Now I'll rewrite the inside here. So 2 plus sine of 3x stays the same, times, now I get to take the derivative of the inside here. Well, the derivative of 2 is going to go to 0, so technically I end up with 0 plus the derivative of sine of 3x is another chain rule. Derivative of sine is cosine, keep that inside the same, times the derivative of the inside there would be 3, then I can close my parentheses off. And of course we don't need to write the 0 plus, I'm just emphasizing that where the derivative of 2 went to, and that was to 0. Okay, we've got 2 more examples in here. So we have example 10, which says y equals tangent to the 4th of e to the 7x. What do you guys think? What rule or rules can we use to take the derivative in example 10? So to take our derivative here, we're going to use a chain rule twice. And I wanted to remind us of something. Your outermost function here is that 4th power, but it doesn't look like it right now. Remember, if I have a trig function to a power, I could rewrite that with the 4th power on the outside and the tangent of e to the 7x all on the inside here. That's a little bit more clear for us to see that our outermost function here is 4. Why don't you guys pause the video and find our derivative, our dy over dx, or our y prime, whatever you want to call it, for example 10. Okay, let's check this together. So my outermost function is the 4, so my power comes down, keep the inside the same. Now to the 3rd power by subtracting 1, so tangent of e to the 7x stayed the same, times, now I need to do the derivative of the inside. To take the derivative of tangent of e to the 7x, it's another chain rule. Tangent's my outside function now, so the derivative of tangent is secant squared, keep the inside the same, so keep the e to the 7x the same, times The derivative of the inside here is another chain rule. So e to the 7x, that derivative will be e to the 7x times the derivative of the exponent there is going to be 7. So quite a bit going on in here. We had the outermost power of the 4, we had this inner power of the tangent, and then an e to the 7x, which in and of itself is another chain rule. So quite a bit going on here. Let's look at our last example. So example 11 says f of x equals cosine of 3x squared minus e to the negative 5x. I want you guys to pause the video and find your derivative in example 11, and then we'll check it together. Okay, let's check this derivative. So I have a composition here, cosine of this other function. So I'll start with the derivative of my outside. Derivative of cosine is negative sine. Keep the inside the same. So all of that gets rewritten times, now I get to do the derivative of the inside. So I'll take this term by term, since I have 3x squared minus the e piece. So the derivative of 3x squared is going to be 6x minus the derivative of e to any power is going to be e to that power times the derivative of that exponent there, which would be times a negative 5. And that negative 5 is only getting multiplied to the e to the negative 5x, not to the 6x. So I want to make sure that when I multiply it, it's just being multiplied to the e to the negative 5x, but then I still have these outer parentheses around the whole derivative, since that whole 6x minus e to the negative 5x times negative 5 has to get multiplied to the negative sign of 3x squared minus e to the negative 5x. Okay, so in this video we learned how to take the derivatives of any exponential functions and any log functions. Specifically, we focused a lot on taking the derivative of e to something and taking the derivative of a natural log of a function. And we also saw how we can incorporate that with our trig values from our prior section, and how we can still use our power product quotient and chain rules as well.